So, hello everyone. Now I want to discuss about the third class of pure substance and the correlation between the macroscopically observable properties and the structure on the tiny scale of atoms or ions or molecules, and also we called microstructures. The third material I want to refer to are metals. As you can recall, this ever important, the most important table in the world, the periodic table, and you can see now with the known about between 110 and 120 elements now, vast majority of them actually are classified as metals. As you can see, you have the main group metals, transition metals, post-transition metals, and the two theories, lanthanoids and actinoids. They're all metals, and they all have distinctive properties, different from the ionic compounds and covalent / molecular elements or compounds we've discussed in the couple of previous sections. So one of the things that you can notice, as you can know in your daily life, metals are all around, and some really observable properties are there. In this case, this is copper, and this is aluminum. As you notice, they are very shiny and with distinctive colors. This is also shiny with this distinctive color. Okay, so shiny with distinctive color. And also a lot of them are kind of malleable, and copper, you can draw them into wires, and this is very important. All the electrical wires in your house, and a lot of transmission lines, and they're all made of copper. This is aluminum pins, aluminum foils. They can really pull or draw or mold it into shapes, so they are quite malleable. Oops, a wrong spelling, so let's correct that. And so this is a quite malleable, or sometimes it's referred to as ductile. So those are something, the properties are quite different from the ionic compound or covalent elements or compounds, as we discussed in the previous sections. So how come? And usually that's the question, and you should start asking asking those type of questions on a much more frequent basis. And as we said before, you probably just suspected, this will have a lot to do with the microstructure of the metals. Let's take a look at aluminum, for example. Let's take a look at aluminum. Take one aluminum atom. As you know, what will be the structure of this aluminum atom? If I ask you to draw a picture, it is very important you develop this skill. We're trying to correlate the microstructures, the properties, the model of those substances, it's crucially important. And as you recall, one aluminum atom, you look on the periodic table, aluminum atom should have 13 protons in its nucleus. And as atom, I would say they have to be charge neutral. As we observe all the metals, they do not crumble and they do not fly apart, which means each individual metal atoms that is the composition, that is the sole composition of the of those metals, and those atoms, they have to be charge neutral. So you have 13 protons. How many electrons you're supposed to have? You're supposed to have 13 electrons. So it's 13 protons and 13 electrons. And we also learned in the previous units, those 13 electrons are actually well organized into what we call it ground state electron configuration. In this case, you have aluminum. You check on aluminum. Aluminum have 3. It's on the 3rd period, which means you have 3 rings. Each ring you would have electrons. First ring has 2 valence electrons. Second ring you would have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, and 8. The last valence electron you should have 3. You'll be asking where this is coming from. Recall you have 13 electrons. Schrodinger's equation and ground state electron configuration will dictate 1s2, 2s2, 2p6, 3s2, 3p1. First ring, second ring, the ring is referred to as principal energy level. Third ring, 2, 8, and 3. 2 and 8 and 3. So then let's actually put the second aluminum atom right by the first one. So the first one, you have this, and let's try to write in 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. You put the second one in, and you quickly notice this is a plus 13, and 1, 2, also 3. This one I didn't do a good job drawing it, so I'll probably will erase it and trying to do a much better job drawing the third one. Similar patterns, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. And the pattern can be kept on going and going and going. So you can ask for another 13 plus 1, 2, 3. So this one, another 13 plus 1, 2, 3. Another 13 plus 1, 2, 3. Another 13 plus 1, 2, 3. One of the things you will notice, those are the aluminum. Aluminum is metal ions. What they tend to do, driven by the octet rule, they tend to lose those valence electrons. They tend to lose those valence electrons, which means those valence electrons are not that tightly bonded to the nucleus, And now we actually can write it in a way, if we write regarding this inner part as the aluminum 3 plus ion, because you do have the nucleus with 13 protons. Now you have 2 rings with 10 electrons. So this is in essence the aluminum 3 plus ion that will be surrounded by the valence shell that has 3 electrons. That will have 3 electrons. So then this one would be actually with all the Al3 plus surrounded by Al3 plus ions surrounded by the valence shell, Al3 plus surrounded by the valence shell. 1, 2, 3, 1, 2, 3, 1, 2, 3. So this is the basic kind of arrangement for metal. For metals, they're composed of metal, composed of the metallic atoms. So next I would like to actually show you a sequence of animation to demonstrate the unique microstructure of metals. In this case we used aluminum to highlight that, and also why this unique microstructure on the atomic level or on the ionic level or on the electron level, and how that microstructure controls the bulk properties we observe. As shown here is the example of metallic crystal, and the metals are all formed on that we discussed in the previous slides. Note this is very similar to that of organization of ionic crystal. They all have the positive charged ions, but in this case we do not have negatively charged ions to counter the positive charged atomic cations. And when all the ions are positive, as is shown here, how could that be? Because they are going to repel each other. Okay, so how could the metals stick together? Stick together actually very strongly. And an anecdotal evidence is, except for one metal, that would be the mercury. Except for that, all the metals are solid at room temperature. But how could that be? And then we'll continue discussion as we discussed before the model for the aluminum. You would have aluminum 3 plus ions, as we see there. This is an example of that metal, aluminum metal. What we call, in this case, we call it subatomic structure. You will have the aluminum particles arranged in an orderly repeating pattern, as you can see here. The valence electrons, as we said before, the 3 valence electrons of aluminum are loosely bonded to the aluminum coil, and so aluminum elements or aluminum atoms, they tend to leaning towards want to lose those 3 valence electrons. Why? Because below that, on the second principal probability level, there are 80 electrons. Now you can achieve the stable octet by losing 3 electrons. Okay. So when you put all of them together, those valence electrons, the electron furthest away from the nucleus, and starts to move freely among here. So they are free to move around and occupy the space between the plus ions, the cations. And the attraction now is what is holding the metal together, is the very strong electrostatic attraction between the positively charged metallic ion and what we call the delocalized valence electrons. Delocalized means it's not localized. It's given ability actually to freely to move around, sometimes to refer to as free moving electrons. So those is still very strong electrostatic attraction. Now, instead of the attraction between the positive and negative ions, cations, and anions, or between the nucleus and the shared electron pairs, this is a covalent bond. Now we're talking about the attraction, electrostatic attraction between the free moving valence electrons and the metallic cation. As you can see, this is a cation. This will be aluminum 3 plus, and you can see the other one, You can see the other one. Now we're focusing on those tiny negative charged particles. We call it electrons, as illustrated here. Now those electrons are free to move around. However, that said, but on average, for each of the cation, aluminum cation, there will be on average 3 electrons surrounding it to make it charge neutral. So now see another bunch of the free-moving valence electrons, another bunch. So now we can actually start changing the model as was indicated in the previous slide. It will be the aluminum 3 plus cation will be surrounded by the free-moving valence electrons. So delocalize the sea of electrons. So the model for the metals are the positively charged metallic cations now is being surrounded by sea of free-moving electrons, sometimes referred to as delocalized electrons. As we noticed before, the metals have some properties, especially the malleability and ductility, quite different from the ionic, either ionic or covalent elements. But how? How could that be explained? And as you recall before, when we talk about ionic compounds, why ionic compounds are brittle? It's because when you move the structure, the microstructure a little bit, the lattice structure a little bit, suddenly the very favorable positive-negative interaction becomes catastrophic, and positive and negative interaction. So they fracture, they just fractures. But that does not happen with metals. Why? And here comes the explanation. Okay, let's look at malleability. And here's the kind of the subatomic structure, microstructure of aluminum metals. And now let's just apply some deformation. Here's the come down, so hammer. If I keep on hammering it, and now I'm start to move everything, including the metallic ions, in this case, aluminum 3 plus ions. And I start moving them, then we'll say, oh, actually those interaction between those ions are actually quite repulsive. But what can hold them together? It still keeps on going. I'm really not stretching it out. So now what we'll notice is, even though the metallic cation starts to move, and now the free-moving valence electrons can actually quickly adjust for the movement of positively charged cations, still maintain the strong electrostatic attraction between those. So they're always holding together any shifting cations. And you can see here, those electrons are free to move around, very agile. And this is the reason why metals are malleable, is because the free valence electrons that can be freely move around to mitigate any movement of the metallic cations will cause. The other thing is about, we talked about it before, the strong attraction between the positive ions in the crystals for delocalized electrons. In addition to the malleability, it's hard and strong and with a high melting point. With only one exception, just remember that. With one exception, will be the mercury. Mercury is a liquid at room temperature, and it only freezes at a very extremely low temperature. So it's actually being applied to using thermometer and a lot of other applications. However, the application of the mercury is on its way out because of the toxicity associated with liquid mercury. So we got sidetracked a little bit, but let's continue the discussion. The strong attraction is causing it to be solid at room temperature and hard and strong because the particles want to stay together. And also in general, the more delocalized the electrons, the tougher the metal. Which means it kind of makes sense. If you have more of those free-moving electrons, and that will be interact, you will have a stronger overall interaction between the free-moving electrons and the positively charged cations. And also in this model, for those electrons free to move around, now you have free-moving charged particles. So conduct electricity, no problem as solid. Okay, so it's the ability to move through the crystal lattice of those free electrons, free valence electrons. The other thing is delocalized electrons, you can readily absorb and re-emit all frequency of light, including the visible spectrum. So actually they are very, very shining characters luster. And you can see here, this is a very famous Chicago sculpture, because Bing, and is made of 100% stainless steel. Now you understand, you can answer the question, why so shiny? Okay, why so shiny? So we finish with this animation. Let's switch back to the continued discussion of the metals as we summarize. Shiny in appearance, hard and ductile and malleable, but malleable in high melting and boiling temperatures. They conduct electricity in solid form, conduct electricity in its molten form. Most are not soluble in water. Some do react with water. You're going to encounter those kind of reactions in type of reactions unit. And we indicated here, the model is schematically illustrated here. You have the metallic cations surrounded by free-moving valence electrons. This is group of metal, that will be group 2 metal. And here comes the explanation. Based on this particular model for metals, the shining appearance we explained by free valence electrons, hard, ductile, malleable, very strong interaction between the oppositely charged metallic cation and free-moving electrons. And also that the ability for the free valence electrons to move quickly to accommodate any changes in the repulsive forces between the metallic cations. So it's enable those metals to be ductile, to be malleable. High melting and boiling temperatures, those are the ones attributed to the very strong electrostatic attraction between metallic cations and the free moving valence electrons. Conduct electricity in solid form, conduct electricity in molten form, all due to the free moving valence electrons. Most are soluble in water, some do react with water. It's also the strong electrostatic attractions between metallic cations and free moving valence electrons, but in some exceptions such as sodium, lithium, calcium, and there's a fairly long list of metals that will react with water. So with that, let's actually wrap up with the discussion about metals. Please consult and attempt to complete the worksheet associated with this podcast. Thank you very much for your attention.